Today I'd like to talk about spin valley qubits and what my team in A-Star has been doing over the last 2 years towards building such qubits in Singapore. Right, so let me begin with Moore's law. I know some of you are sick of this, but if you look at the information technology that we have become so used to, perhaps it's not too far-fetched to say that it has become indispensable, right, in terms of how we live, right, how we work, how we play, and even how we eat now. Most of you now can order your food, your lunch from a mobile app. Yeah? But all this is thanks to the fast network that we have and also the computing power that's available. And where does this computing power come from? If we think back, you probably agree with me that we are all beneficiaries of this relentless advance of Moore's law for over 50 years, right? And, well, if you think about it that way, right, then it's not surprising when you see notices such as this on the demise of Moore's law, right, some emotions may be stirred, right? But as human beings, there's always a group of us who are in denial. We don't want to see Moore's law go away, right? And there are some who are undecided. There are some who say, well, you know, don't talk about it, just don't look at it, right? Let it be dead or alive, who cares? Let it be. Maybe, and that's a way to keep everybody happy. But right, if you think Moore's law is at the bottom, and something it is, right? You ask people in the industry, most of them will tell you that silicon CMOS will likely still be around for a couple of decades. Why? Because the infrastructure is built, right? It's very difficult to change overnight, right? Even if you have the best quantum computers coming up, right, it will take some time, right, to go mainstream. So in the near future, what the scenario looks like is probably more like this, right? You have silicon CMOS still mainly as the bedrock for general computing, but on top of this bedrock, you have specialized processors, and you already have CPUs, GPUs coming in for a long time. And more recently, you have AI, neuromorphic chips that come on. And in the quantum community, we obviously would like our quantum annealers, fully programmable quantum logic circuits to go on as well. And I'm sure there will be more. Right. We don't know what the future holds in terms of the other devices. Perhaps atomic clocks as well can go on this as well. So there's still plenty of room, even at the bottom, as we have been told. Now, the recent urgent challenge in this area of quantum computing seems to be the race for supremacy, to show that the quantum computer can be useful. And by useful, that means that we have to surpass the capability of the classical computer. And I think you've seen some mentions of this already in the morning. Right, I list for you, the news reports coming out from IBM, Intel, Google. This was kind of at the beginning of last year because they had a deadline to show supremacy, I think, by the end of 2017. So everyone was rushing for deadline. I think Intel and Google missed that a bit. But then late last year, right, almost at the close of the year, IonQ won up everyone with this 160 ion qubits. But if you read the report more carefully, right, they claim that they could only do full computation only on 11 qubits. All right. Okay, I think think my pointer is not really working. And not to lose out, right? IBM recently announced their first commercial quantum computer at the annual tech show CES 2019. But scaling up the number of quantum qubits, qubits is not the only thing in terms of upsizing. There's error correction to contend with, and I think there's already been some mention of it this morning. Right, and Google kindly puts up this very nice blueprint. Okay, sorry. Yeah, thank you. So Google kindly put up this blueprint just last year. This is their strategy, and they're trying to go from few qubits to, in the near term, right, showing applications that exceed classical computing, right, with a few hundred to perhaps 1,000 qubits, and hopefully in future going to many more qubits. Right, in A-star, we are privileged to have some funding, right, and the RIE 2020, this is a funding tranche from the government. And in this particular funding tranche, we have some funding, right, to develop some capabilities that are relevant for Singapore to exploit the opportunities that are coming up in terms of quantum computing. Within this program, right, we have 5 projects, right, targeting eventually an integrated effort towards scalable logical qubits. And within this program, I lead the spin valley qubits fabrication, and we're making this out of 2D materials. And the main thing we're looking for is scalability in terms of numbers as well as in terms of process. Now, of course, spin qubits are not new, right? And there has been many variants of this reported over the last 2 decades, perhaps, right? And here I show you a brief survey of some of the common ones, and notably you see that the quantum dot defect qubits are quite popular, but more recently we also have qubits, right? They are built, right, by gating carbon nanotubes to form quantum dots as well. Right, so let me get on to our work. Right, for our project, our main objective is to demonstrate the first spin valley qubits, right, using a scalable technique, right? And by scalable, we mean we want to be able to use wafer scale compatible technologies for both the growth, and the fabrication processes. Right, the qubit architecture is based on electrostatically-gated quantum dots, right, for the qubits. And then we have either an SET, a single electron transistor, a quantum point contact that we use for our readout. Now let me go a bit into the material system that we're using, because this material system is important for why we are making this kind of qubit. It's quite new. And this is based on 2D material, which I'm sure you know, right, has been a recent revolution in terms of materials. Now, after graphene, this new class of 2D semiconductors known as transition metal dichalcogenides, or TMDCs in short, right, is catching a lot of attention in recent times. Now, these materials are semiconductor and direct bandgap semiconductors in nature. And what is interesting about them, right, is that they are made up of a choice, right, of a transition metal and a chalcogen species in their crystal lattice, right? So you can choose the transition metal to be molybdenum or tungsten, and the chalcogen could be sulfur, selenium, or tellurium. Right, because these crystals form in this way, right, adopts this 3-atom thick structure, and also because they have dissimilar atomic species, you find that these are non-centrosymmetric crystals. And by that we mean, if you look at a crystal, there's a lack of spatial inversion symmetry within these crystals. Right? In addition to that, the heavy metal ions that's inside, right, gives you a strong spin-orbit coupling or interactions within these materials. And if you combine these conditions of the lack of spatial inversion symmetry, strong spin-orbit coupling, you actually get a very unique feature in this particular material. They have a unique spin-valley coupling, and so if you look at this 3D visualization of the band structure for such a material, then you find that the spins with the up spins, right, can only reside in the blue valleys labeled by K, and the down spins can only reside in the red valleys labeled by K prime. Now this spin valley locking, as it were, right, is expected to give you, right, robust qubits, because if you want to scatter, right, one of the spins from K to K prime, you also have to change, flip the spin at the same time, right? And that is seen as, right, a prohibitive process. Now, all of this paradigm comes a number of proposals for making qubits out of these systems. And I list for you two, right, proposals in recent times. One based on a single layer TMDC material, and one based on a bilayer architecture. So the first one is the proposal from Guido Burkhardt's group in Constance University. And this one is quite simple. You put down electrostatic gates, form your quantum dots, and then your qubit states, the two levels are the valley-coupled Kramer spin states, right, at the conduction band edge. Right? And these states are hosted within the gated quantum dots. Now, you tune these levels by using a perpendicular B field, right, out of plane, and the qubits, right, can be coupled via exchange interactions. Now, in the bilayered architecture, the qubit states are hosted, right, within different layers, right, the upper and the lower layer. So you find that these states can also be tuned by an out-of-plane, right, magnetic field or electric field. And if you want to flip, right, the spins, right, you can use an AC magnetic field in plane. Right? Now the interesting thing here is that if you look at this, right, at the K valley and the minus K valley, the level splittings are different. And what it means is that they correspond to different resonances, which means that you can address, right, the qubit at the K valley or the minus K valley independently. So this selective spin flip capability, right, allows such an architecture to achieve what they propose as a valley C0 gate. So how do we build these things? Right, we first need to start with growing very high quality TMD materials or TMDC materials. Then you deposit a suitable dielectric, right, which you need in order to do the gating. And of course, finally, you do all the lithography that you need to put down the contact gates, the contacts for the source and drain, and also the top gates needed to create the quantum confinements for your dots, as well as the peripheral readout electronics. Now, it all looks very simple, but hidden within each of these steps are a lot of challenges. And so that's what my team has been engaged in the last 2 years. So first, we have to master how to grow these materials and not just mechanically exfoliate them, which is quite a common practice at this point in time because it is difficult to grow high-quality materials like this. And to date, right, within IMRI or within A-star, we are able to grow continuous single layers up to about a centimeter square. Not huge, but sufficient for us to make devices or begin making devices on them on different materials. But just because you can grow nice single layer crystals does not mean that you have the material you need, right? Because if you remember in these materials, we really would like to exploit the spin valley coupling. And the question then is, if you grow the material, can you guarantee that spin valley coupling is still there? Right. So for that, we use a method called circular dichroic photoluminescence in order to help us check the materials that we grow. And so in this particular view graph on top, we look at one particular triangle, which is grown over here, where the growth is less uniform, and over here, where the growth is a bit more uniform, and you characterize them. Now, if you look at just the red curve, the red curves, right, gives you a sense of the degree of valley polarization, which is an indication of the presence of this spin valley coupling, right? If you do a spatial map over the area that you're studying, you can then look at the uniformity of the material, right, in terms of this spin valley coupling. Now, once you have the material, right, you want to put down gates, contacts, right, so that you can complete the devices. Right, in order to make contacts, you need to put down good, right, ohmic contacts, and it's not just ohmic, you need low resistance as well. You need to have a back gate, and this is usually a given because if we choose highly doped substrates, right, then you do have a back gate naturally on the substrate. You need a good dielectric layer, right, which interfaces well with your 2D material. But at the same time, right, it's compatible with the gating structures that you're putting on top in order to provide effective, right, electric field control such that you can create the necessary quantum confinements. And finally, of course, you need the capability, right, to put down electrodes which are tiny, thin, right, of the width of a few tens of nanometers, and so you need good lithography. And so these are the things that we've been dealing with in the last 2 years, trying to optimize. And so these are some of our first device results coming from this work. Right, so these are initial materials, are devices that we made, and unfortunately, I can't show you devices that are made on grown materials yet because when we were making these devices, we didn't have the growth processes optimized yet. Right? Actually, we don't have it optimized currently as well, but we have some decent growth. But these initial devices were made out of exfoliated few-layer TMD materials, MOS2, WSE2. And I guess the upshot of it is that we were able at 4 Kelvin, a temperature of 4 Kelvin, and if you know about these devices, this is quite a high temperature to be trying to measure quantum confinement in these. We find that we are able to pinch off, right, the current between the source drain going through these devices, and that is an evidence that we can actually close the dot, right, or open it. But at the same time, as we close the dots, we find that you start to see evidence of steps in the current or the conductance. Now, this evidence of steps basically gives you indication that you are entering into quantum confinement in these devices. Now, in parallel with fully gated, top-gated quantum dots, we are also exploring the possibility to create these quantum dots perhaps in a slightly simpler way, in terms of gating, right? Why do we do that? If we can etch the 2D material down to ribbons, you already have, right, physical confinement from the start. And if these nanoribbons, right, are then gated with top gates, right? And hopefully fewer top gates, you get your quantum dots as well. So we hope that this method, right, could help us simplify the overall architecture. But of course, it does come with its own challenges. When you do etching, you create damages in the edges of your ribbon. You have edge states, right, coming from the dangling bonds. You also have contamination coming from the processing, and perhaps all the irregularities that come from a process that might not be fully optimized. So we asked ourselves if this could be done, and so the first challenge of us is for us to etch this into ribbons. We have done it down to about 50 nanometers, and the idea, right, is to characterize these ribbons in terms of transport to help us understand their quality and if these materials after etching would still be viable for our use. Right, so happy to report that in a recent paper we have shown that these ribbons that we've etched down to 50 nanometers can attain mobilities as high as about 50 centimeters square per volt second. And in fact, as far as we know, is the highest reported to date for such nano ribbons. We also find in the devices high current on-off ratio. We're not planning to use this as transistor, but this actually is a good side outcome. And we find that even with a back gate, we are able to achieve fast switching of these devices. Right, so this is all well and good, but we have to start, right, making these dots now and measure them and operate them as qubits. And so for our initial characterization of these devices, we use our 4K, it goes down to about 3 Kelvin, but normally we operate it about 4 Kelvin. For our preliminary assessment of these devices, we would usually use this 4K cryostat. And once we verify that these devices are indeed working well, right, the plan is to move them over to our dilution refrigerators to do the more detailed characterization and study, and hopefully operate them, right, as qubits in time to come. Now, as we speak, our 2 dilution refrigerators from Blue Force is being commissioned. They're working very well. These are the latest generations from Blue Force going down to below 10 millikelvin as a base temperature. And we were told by Blue Force that the system they delivered to us is the first in the world with active vibration damping and also a fast sample exchanger, which you can see is bottom loaded. Right, so with these 2 systems, we are now ready to really take on the full cycle of optimizing these devices. So I want to give you a little taste of where we stand with respect to what's going on in the rest of the world. We are obviously not the only one doing this, and so if you look at one of the earliest reports, and perhaps that gives you an indication of when they started work on this, probably way before 2015. This is a group by Kuan in Hefei in China. Right, and so they first reported few layer quantum dots made on WS2, WSE2, using an ALD oxide. Right. Yeah, I forgot to mention that actually we are using an ALD oxide because we want to have a scalable process. In contrast, there are other groups like Philip Kim's group in Harvard is trying to make the best devices possible, and so they encapsulate, right, the MOS2 between exfoliated HBN or hexagonal boron nitride. Now these gives you the best devices that we have seen so far, but the question of whether the processes, right, the exfoliation, the stamping can be scaled up remains to be answered. Right, and most recently from ETH Zurich, Enslin's group, which is very well known for low-dimensional transport experiments, have published their first MOS2 monolayer. So this is finally on a single layer, monolayer device in applied physics letters. So we are following hot on the heels of these 3 groups right? And we have our first devices and first papers reported this year. And I put here a view graph at this lower right corner as a teaser for you, because this is what we think, right, are Coulomb blockade measurements coming from one of our devices, right? We're going to measure this more carefully in our dilution refrigerators, but stay tuned, right? Okay, so in summary, let me just show you this chart, which essentially summarizes the process flow that we have established. We probably have to go through several cycles of this, or even more, before we get the optimized devices and start to be able to manipulate the qubits on these materials. All right? So before I end, I think it's appropriate for me to acknowledge the team that's working very hard with me, and without all their hard work, dedication, all this would not have been possible. Thank you for your attention.